So what we have done over here is, so first of all we have created instance of class q, and then we are performing in q operation thrice. So one will be added first, so one will be like head element, then 2 3, so we are getting array of size 3, 1 2 3, and then we are like performing pick operation once, and then we are like deleting this thing. Since we have started with like means none, so that's the reason when we do pick it will be like showing us that means starting element, okay, because we have initiated head to be none over here. That's the reason we are getting none as like head element for now. And then we are performing dq twice, and that way like this means that thing will be deleted, and we are, when we print this thing we are getting like 2 and 3, none and 1 will be deleted, and like 2 and 3 is something we are getting over here. Okay, so this is entire queuing, means this is how we can perform or implement queue using arrays. Okay, I hope this thing is clear to you. Lucky, Kripanshu, is this thing clear to you?
Yeah, it's clear.
Yeah, it's clear.
Okay, so next thing is implementation of queue using linked list. So because we mentioned, right, stack and queue is something we can perform either using arrays or like using linked list. Only difference between stack and queue is stack is something which follows LIFO principle, that is last in first out, means last element, addition will and deletion will always happen at like top layer or like at last element, whereas in case of the queue addition will happen at tail end and deletion will happen from like head end. Yeah, that's something happen. So basically whenever we have to implement queue using linked list approach, first of all we need to create individual elements. We need to write a class with instance variable data and pointer next. Then we need to create second class, that's something will like initiate our linked list with variable head and last. So thing is that in case of the, so instead of calling that as like tail, what I'm saying is like I'm calling that as a last. Okay, so basically these are the two things that we need to maintain, because in case of the queues, in case of the stack we just maintain one variable top. In case of the queue, when we have to implement that thing we need to maintain two variables, head and tail, or like head and last. So basically each time you add element, last variable will be incremented, and when you delete element, head element will be incremented. So using this thing you will have sense where exactly you are, means where exactly your queue is. Okay, so you need to create class, and that's something will initiate both the head variable and tail variable or last variable. The next thing that you need to do is you need to appoint head element to the first element, and then you need to, I'm talking about like means absolute beginning. So you need to point head element to first node, and then you need to say, okay, my last element is also equal to first element. Okay, so that's how you get particular queue started, and there onward, whenever we have to, and there onward, whenever we have to add elements. So basically, this first thing is, that's how we have defined node class, and we have like instantiate this particular class with these two variables. Then next thing that we are doing is we are like created class queue, or basically we are created that we have created a linked list with sense of like two variables, head and last. And initially we have begin that thing with like just none only. Okay, data type. In queue operation is something when we are adding element at the last point. Okay. So what we are saying, whenever our last is empty, so in that situation means whenever my queue is empty, I will say means my first variable self dot head is equal to node data. Okay, so basically I'm creating first element and I'm pointing that, means I'm storing that as my first variable or like first element. I'm storing that thing into self dot head. Okay, and then I'm saying my last element is also equal to first element. Okay, basically there is only one element inside that queue, and that same element will act as a head and same element will act as a queue. So this is something when there is no element inside that queue, but whenever there are element inside queue, that's something we are checking over here. Whenever there is like none, that's something we will do. But whenever there is like element over there, in that situation what we will do, in that situation we will increment our last or tail element, tail variable by one. Okay, so cell dot data, cell dot last dot next. So that's something we will do. So we are pointing this element last to next element. Okay, so this node data is basically like second, the element that we are trying to add over there. Okay, and then what we are saying is like cell dot last, now my last element is like the element that we have added. Okay, I hope this thing is clear to you. So basically this is a like increment operation. Basically this is a enqueuing operation. So whenever it's completely empty, what I'm doing is I'm creating means I'm creating one element. I'm saying like this element is equal to head, and I'm also saying like my last element is also equal to head element. So basically there is only one element. But whenever there is like element already there inside that queue, in that situation what I'm doing is I'm incrementing because what we were saying, like element is always being added from like tail end. Okay, so last variable should be incremented. So and whenever we are saying I have to increment that thing in the in the case of linked list, we need to use next variable. So we need to point it to next thing. So in case of like arrays or something like that, we have indexes, right? We increment it like using one. In case of the linked list, we need to use pointers over there. Okay, so what we are saying is like this cell dot last is like my last element. So now I am pointing it to like, it will point it to like newly added element, and then this cell dot last dot next. So that something will act as like my last element. So that something is happening over it. Okay, I hope, and that's how this enqueuing operation is being done. Then there is a dequeuing operation. So dequeuing operation is one where like element will be deleted from the front end. So cell dot head element should be like means that thing should be like deleted. Okay, so what I'm doing over here, so I'm checking like cell dot head is a none. So basically I'm saying whether my queue is empty or not. Whenever it's empty, so whenever cell dot head is none, means that's how we are initiating our linked list. So it will return none. Okay, means there is no element in head location. But whenever there are elements in that situation, so what I'm doing is like deleted element is equal to self dot head. Then I'm saying like increment my head element by one and save that as like my new head. So self dot head dot next will be saved as a self dot head. Okay, that's something you can see over here. I hope you are getting visualization for that thing. So that's the reason I'm saying keep two variables in your mind: variable for the head and variable for the tail or last variable. Whenever you are doing addition, increment that last variable by one and store like one new element over there and create that as like new next variable self dot last. Whenever you are deleting that thing, so self dot head will be like deleted element. Point that means wherever that first element is pointing to will be your like next head variable. So cell dot head dot next will be your next new cell dot head, and you will return that like first element. Okay, so this cell dot head dot data will be like returned, and using these two things you would be able to like create queue. So you can just like create queue using this instance queue and aq. That something will allow you to create instance of that queue, and then using this enqueue and dequeue thing you can like either add element over there or you can delete this thing over there. Okay, so it's quite interactive over here. So you can just like you can run it and you can just type like okay enqueue 15 or enqueue 10 or dequeue. So if you just like type that thing, it will like do that thing like enqueue 10. So it will like add that thing. Then if I say enqueue 20, it will like add one more element over there. Then if I say like dequeue, it will like dequeue element. If I say queue quit, in that situation, that means break will happen and it will come out of that thing. Okay, and if I like means if I run this new variable like print, then I would be able to like get that entire operation. So basically what if I use that method that I was saying like how to read linked list, like you will create new method, then you will check whether means head is existing over there or not, like if self dot head, then you will go inside that while that head dot or like temp dot next over there or not, temp is equal to self dot head. Then you will go through that temp dot data, and then you will point that temp to next. So that way you can print that thing. Okay, but basically this is implementation of queue. I hope this thing is clear to you. You need to maintain two variables, last and head. Whenever you have to do enqueue operation, you need to increment that thing by one, and you have to store that as like your next new next new last. Whenever you have to do dequeue operation, you need to delete cell dot head, you need to increment it by one, and you have to say that as like your new head. So basically this is a dequeue thing. And whenever you have to like read first element, you can just like start with like cell dot head dot data, and that's how you can read that. Means peak, you can perform that peak method. That's all about queue thing. Okay, means how exactly you can get it implemented using queues, sorry, linked list using this head and last variable using these two variables. And in case of the arrays, you can directly use append, and you can use pop 0. And whenever you have to observe what's the first element, you can just check like storage 0, and you can get this thing done. Okay, but this is how we can implement queues using linked list and arrays. I hope that thing is clear to you. Lucky, Kripanshu, and Atharva, are these things clear to you?
Yeah, it's
Yes.
clear.
Yeah.
So then there are certain non-linear elements. Okay, so there are certain non-linear data structure. So basically, as I mentioned, this is hierarchical data structure where all elements are like present in hierarchical fashion. And in case of this non-linear data structure, there are certain properties which are quite unique. Okay. So in case of the tree, it carries sense of like starting position. So this is for head. Cycling is not allowed through that structure, and it means each location you will carry two things. For each element is something we are calling as like node, or node is something we will call that when we are talking about trees. Let me go to that thing now. That thing will be gone. But yeah, thing is that tree is a hierarchical data structure. It's again non-linear or unordered data structure. All the elements are like present in hierarchical structure at different levels. Okay, and each primitive element will be called as a node, and all those nodes will be like related to each other using like certain branches. So the way we see tree in real world, so it's similar to that only. But that tree is something, the tree that we see in real world grows in like upward direction. The tree that we use in case of the programming, it grows in like downward direction. Obviously we can grow it in any direction, but thing is that like if you consider like in general sense, like at the top you will see like root node. So as we see in real world, like root is where like tree starts, right? In case of the programming also, we start with root node, and then it grows in downward direction. From that root it sees branches, means shoot comes out, and then you will see like certain branches over there. So yeah, can you give it a minute? Yeah guys, sorry for interruption. So thing is that in case of the trees, means from that root shoot comes out, and from that shoot branches will come out, right? So that each branch will like hold like certain leaves and all that stuff. So that's something will be considered as like nodes. So thing is that in case of this tree data structure, we will have like root node, and then from that root node we will, I mean, certain branches will come out, and then there will be like again nodes, and that will further branch out, and like there will be like more nodes. Okay, so thing is that tree is a data structure where we have like collection of all these nodes. Okay, and for each node it will carry two things. Okay, so basically there are like three things which exist over there. So thing is that we will just like talk about two things for now. So first thing it will carry certain data, okay, or value, whatever you prefer. And then second thing it will carry references to child nodes. Okay, so we are saying like from each node branches will come out. So for each node there will be certain references to the child nodes. So whenever we have to implement tree, the first thing that we need to do, we need to create node. It means we need to create class node. That's something will act as a node of our tree. And then we need to create certain, means we need to instantiate certain variables. Okay, so first of all we need to add value to that particular node. We need to add references to left and right branches. Okay, so you can add like as many as branches over there, but since we are talking about, means we are restricting our discussion to like binary tree only, that's the reason I have just added left and right. But you can add like as many as branches over there. Okay, you just need to make sure like you are carrying proper pointer for that particular node. Okay, so that way you can do this thing. So basically this is the first thing that you need to do. You need to create class node, and for that particular class you need to add certain attributes. First attribute should be data, and then other attributes should be pointers to child nodes. So here we are like having like this, for this particular node we are adding cell dot value is equal to value. We are considering like there will be like two child nodes, so that's the reason we are pointing cell dot left is equal to none and cell dot right is equal to none. So this is how we are creating one node inside that tree. Okay, the second thing that we have to do is So that's the first thing that we have to do when we are dealing with like implementation of tree. The second thing that we have to do, we have to, as we were saying, like in case of the way we are having head element inside stack, or we are having head and last or tail element inside queue, in similar way, in case of the trees also, we need to create one more class called like binary tree or tree, and we need to instantiate that tree using certain variable. Okay, so basically we need to define where exactly that tree begins, and that will be like root node. Okay, so we need to define that root node. So basically that's something we are doing. Self.root is equal to node root. Okay, so node root. So that's something is happening. So that's something we are doing over here. Until this point means if we do this thing means we are good. Okay, next thing that we need to see is like means even if we do this much thing, means even if we define like these two classes, means we can implement this tree. Okay, so let me show you how exactly we can implement this thing. Don't think about like these other methods for now. Okay, you will be lost. Just think about like first those two classes. So whenever we have to create tree data structure, what we need to do, we need to call that tree data binary tree class. Okay, with one. Basically we are creating root node with value one. Okay, because you see over here self.root is equal to node root. So using that node, in case of the stack or means that queue, we were just using like none or head is equal to none. But over here, we are initiating root with proper element. Okay, means it's quite different over here. Okay, means in definition itself, we are doing this thing. Means that's something we were doing over there only. But in definition itself, we are like beginning this thing with like certain thing. Okay, so using this thing, we are like creating this tree. Then what we are doing, tree dot root. So basically that's like because we have created variable self dot root is equal to node one. So what we were saying is like our tree will have like inherent variable attached to that, and that will be root, and that will be equal to like one. Okay, so since that is an element and it has like two more variables. Okay, if you go to like this particular first class, then what we were saying, like each node will have like three things. So root dot data is equal to value, but it is also having like two more things, left and right. Okay, so root dot left is something will like give access to like left branch, and root dot right will give access to right branch. Okay, so what we are saying is using binary search one, so we are creating root node, and that will be stored into tree. Then using tree dot root dot left, we can define left branch, and at that point we will add one more node. Okay, node 2. So we are attaching that. Then root dot right, we can add like one more element. To root dot left, we can add one more element, and node 5. So basically this is like kind of balanced tree. Okay, means in terms of just like the way we have added all those elements, but otherwise means the way we see values or data over there, it's not that balanced. Okay, but yeah, so this is how we can create this tree. And if I just like if I just print this thing, whatever I have created, you would see this tree to be like 1 2 4 5 3. Okay, so here I have like also there are ways in which we can like read data from tree. Okay, so basically you can go for DFS fashion, like depth first fashion, or like breadth first fashion. So basically we are going in like depth first approach over here. And since we are like creating these things, so what we are saying, like one will be like root node over here. Then from there will be like two branches, left and right. For left branch I will add two over here, and from that two I will add like one more node, and that four will be over here. Okay, and from at right branch I will add like four, sorry, I will add three, and then from three I will add five over here. Okay, so whenever we are reading it using depth first search approach, it will go in like left branch first, and then it will come back and it will go in right branch. That's the reason it will going for one, two, then four, and then three and five. Sorry, yeah.
Hello.
Yeah.
Yeah, here you have mentioned like tree dot root dot left. So this is on the left side, but on the left side only we have to write add 5 now, because root dot left dot right is there. It's not root dot right. Is it like that?
Yeah. Means left dot right means it's not balanced tree. That's the reason. If you see this
Like
implementation over
4
here.
and 5 will be on the same side of like
Yeah,
4 and
yeah,
5 will
same
be
side,
the
same side, same
child
side.
of 3 na.
Yeah,
Child
same
of 2,
side.
sorry.
Yeah,
Child of
same
2.
side.
Yeah. Okay.
Yeah. So one over here, then left node will be there 2. From that 2, there will be 2 node 4 and then 5, and we will go back all the way to 1, and then we will have 3. That's the reason it's showing like 1, 2, 4, 5, and then 3. Seeing this thing?
Yeah, I got that.
Yeah.
And
Yeah.
one more thing, like while initializing this root dot left, root dot right, we can initialize as per our own convenience. Like we can do root dot 1, root dot 2, root dot 3. Then if you want to make 3 child nodes, then we can do like that, na? Root dot 1, root dot 2, root dot 3.
Yeah, yeah,
Then if you
possible.
want to go from 1 to another, like root dot 1 dot 1, like that.
Yeah,
We can
yeah,
continue
we
like
can do that. We can
okay,
do that. Root dot 1, root dot 2. That's possible. I told you, right?
okay.
But that something should be there in your first class definition itself.
Yeah. We have to initialize that in the first class.
Yeah, node class
Okay,
itself.
okay.
So
Yeah.
that's how we like generate tree data structure. Next thing is when it comes to tree data structure, there are two things. Like we should be able to read that entire tree using the DFS approach or BFS approach, and then we should be able to insert element over there. Okay. I believe insert is something, yeah, search is something we will see for this. Okay. So whenever we have to do search, so we will use this method. So this method is something we'll take tree.root as argument, and final is find value. So basically we are looking for particular element inside that tree. Okay. It's not about like adding element. It's now about finding particular element inside that tree. So this thing should be happen like really quickly. Okay, because if you are going for like these arrays and all that stuff, so in that situation it becomes quite complicated. Okay, like it will be of like big O of n kind of search operation. Okay, in case of the tree, in worst case that will be the case. Okay, if you have to go for like entire DFS thing, but there are certain things using which we can like expedite that thing. Okay, means if you go for like means if you just convert that into like big heap means sorry, mean heap or max heap kind of thing, then in that situation it will become quite easy to do this searching quickly. Okay, so it will be I believe n log n or something like that operation. But yeah, so this is a pre-order search. This is a root node, and this is a find the value that we want to find, and then that's something we'll call this thing. So what we are doing is whenever my start value is basically for each node we will have like three properties, right? Three attributes: value, left, and right. So value will store our value. So basically whenever my value is equal to find the value that we want to find, it will say okay, that element is something we have found, and it is like at that location is something we are not giving out right now, but it will say like this element is something we have found. If we don't find that thing in like root node or like parent node, then we will check for child nodes. Okay, so it will go into else loop, and it will perform two operations. So pre-order search with left node as a like root node, and it will try to find that value, or it will go into right node. Okay, it will check both of these things simultaneously. Okay, as a or thing. So if it sees like in left node also that thing means whenever it call for this thing, basically it's calling the same operation again. So it will go check that thing. If this thing is not available there, it will go again into check both the nodes, left node and right node. If it go again, it will go into left node. For left node, it will again check that thing whether it equal to the value that we want to find. If not, then it will again check left and right node. So basically that way we will like go through entire tree. Okay, because here we are also checking right branch as well. So this is how we will do search thing, and whenever we have to do printing thing, so basically we are performing like this DFS approach over here. Okay, so DFS is like first of all we are checking left, so pre-order print. So basically there is a print operation. From that we are calling this tree dot root, means the starting node as like argument, and then we are like means basically we are returning this as like array. Okay, so that's the reason I'm saying like give me all the element inside that array. So first thing is like I'm initiating this thing equal to traversal plus start value. Okay, so the whatever value we have inside that start node, that something will be print over there. Then uh, then second operation that I will perform is like whenever there is a root node available, I will check. I will read value inside root node. Then I will read value into left node, and means it will call this traversal means it will the value that we have stored inside this traversal variable, and it will return again new since we are creating it to be like some sort of array with like basically we are creating it to be like some sort of collection of like strings only. Okay, so means it will return like that thing further, means once we check like left branch, then we will check right branch. So basically we are we are doing this thing, and then it will return like our this final array, traversal array, and that's something we are returning means entirely or to this variable method. Okay, and yeah, so that's how we are getting this particular thing done. So whenever I call like tree dot search is equal to 4, so it will go through that entire tree and it will try to find whether 4 is there or not using the DFS approach or the approach that we mentioned, and it will return 4 or means true or false. Means if I had like added that print is equal to tree dot search for, then I would have received like a true or false command. And when I print that thing, so it follows this traversal thing approach, like it first go into like a root node, then from root node it goes into like left branch, because that is the like convention, like you go into left branch first and then go into right branch. Whenever you have to add element in left branch, you should have like small element, in right branch you should have like bigger elements. That's something you have convention that we follow. So it goes into like left branch, it will like increment append that array with like these values, the value that we get over here. Then it will go into like right branch and it will check over there, it will then again go inside that first thing, and we will keep doing this thing, because what we are doing is we are basically calling these functions again. Okay, pre-order print function is something we are calling again and again and again. So that's the reason it will like go through all the left elements, and for each of that left element it will like go into left and right and then left and right and all that stuff. So once, as long as I'm not done with all the left element, it will keep going until last point. Then for last element it will check to right, and then it will come back at the like root node and it will go to right branches. So a recursion kind of thing is happening, but in terms of functions only. Okay, so this is how we are printing and reading, searching for particular element. Now we are talking about binary search tree. Okay, I hope like you guys are clear about how exactly tree should be defined, and how exactly we can do searching operation, and how can we do printing operation. Okay, means how can we read all the elements. I hope you guys are clear about that thing. Next thing is binary search tree. So in case of the binary search tree is like specialized form of tree where for each parent node there will be just like 2 child nodes. Okay, so here again we need to create a node class with certain variable, means like value left and right. For value we will store some the value that we want to store at the particular node, and then we will carry references for left child and for right child. Okay, so this is something we are doing over here. The next thing that we want to do is we want to initiate that tree with certain root. Okay, so root is equal to node into data. So with certain data we are like initiating root, and the next thing that we are doing is like we want to see how exactly we can add element to that binary search tree, and how exactly we can remove element from that. Okay, so this new value that we want to add, and we will call this insert helper function inside this insert method, and this method will like call this entire thing. So basically what it will do, so new value is like the value that we want to add, current is like the current node that we are at. Okay, so cell dot root is something we are providing. Basically we are saying like we will start with like root node, but insert function can take any node as an input. Okay, so if it takes like root node as an input, so root node and new value will be taken as input. Root node will have like 3 things: value, left point, left reference, right reference, and like new value. So value that is existed or like which is present at like root node will be compared with new value, and based on that it will decide whether I store new value into left branch or right branch, because it has to follow certain convention, right? Convention is that like in left branch small value should always be there, and in right branch bigger value should be there. Okay, you can check over here. So if current value is small than new value, so in that situation I'll go for like right branch. Okay, because it's smaller, so it's saying like since my new value is bigger than like that parent node, so it should go into right node, right branch. If it's smaller, then it's saying like store it into like left branch. Okay, so that something is happening over here. Whenever my current value is greater than new value, in that situation we will like add value to new sorry left node. Okay, but yeah, this is the insert helper operation. Whenever I have to do search, I will again start with root node, and like again there will be thing. So it will like checking current thing, means whether there is a node exists there or not, and for each of that node it will check value, which is and it's checking whether it's equal to final value or not, the value that we want to find or not. And if yes, then it will return to be true. If not, means there are two if condition. Basically, it's checking both the branches, right branches and left branches. So this is how we are expediting our entire, or like increasing speed of our search. Okay. So basically, what we have included this one more condition, and that something will like increase our speed by like many folds. So this is something is happening. Okay. And this is how we can do this search much quicker, in much quicker way. And then traversal also, it will follow the same approach that we were doing earlier. And this is how we can generate this binary search tree. So this is how we are creating initiating that tree with certain root, bst4 means value to be 4, and that's how we are generating root node. Then we are adding, because we have insert thing over here. Okay, here not we are not saying whether you add it to like left or right. It will be decided inside this logic only. Okay, whether based on the value of that the new value that we want to add, and its relation with the value which is present at that root node or parent node. So based on that, that element will be added to either left branch or right branch. So we can just like create tree using bst4 and using tree dot insert, and we can add element over there, and based on this comparison that entire tree will be built. So we are trying to add 2 1 3 5. So basically if we had added this thing earlier, then like if 4 were like our first root node, then 2 go into like left branch, then 1 will like go into like, means we have to define where it means root dot left or something like that. But over here in this binary search tree, based on that logic or implementing the logic that is expected for binary search tree, that those elements will be added, and then we can print that thing. Okay. And yeah, this is the way in which like that tree is like developed. So 4 is something that we can see that's like at root node, and then there is a 2 1, and then there is a 3 5. So it will read in the DFS fashion only. So what it basically saying is like, is the 2 is like less than 4, so that will be added into left branch. Then 1 is further less than 2, so it will again add into like left of that 2 node 2. Then 3 is greater than 2, so it will be added into right of 2. And then 4, then next element is a 5, so that element is greater than 4, so that element means that element is greater than 3, so that element will be like go again at level 2, then it will again go back to level 4, and that will be added to right. So that will be like unbalanced kind of tree, but it will again binary search tree representation. So yeah, and then we are checking 4 and 6. So 4 is there, 6 is not there, so true and false is something being written. I hope like this tree binary search tree thing is clear to you guys. Is this Kripanshu,
Yes,
Lucky,
it's clear.
Atharva?
Yes, it's clear.
Yes.
Next thing is that like we are discussing about trees, but thing is that with trees, search is something. I mean, obviously, search is something can become really, means addition and deletion is something become big with trees, but search will still be like quite. I mean, in worst case will be equal to array only. Okay, means search complexity. Okay. So that's the reason what we tend to do is we go for like we try to convert this tree into array. Okay. So if we have to do that thing, then that operation will be considered as like the final data structure that we get, we call that as like heap data structure. So basically that is like at backbone or at the bottom we are having tree presentation to store all that elements, but just to like access that element, just to do that searching and sorting thing, we can like present that thing in the form of heap. Okay, but there are two kinds of heap: mean heap and max heap. So mean heap is where we are having minimum element in parent node as compared to child node, and then there is a max heap where we are having like maximum element in parent node as compared to child nodes. So the first operation that we are seeing over here, so basically we are really not going for means uh, because thing is that in case of this heap thing, we are seeing like min heap and max heap kind of representation. So each time that data should be manipulated properly and should be added on right branch. Okay, so that's how we get this heap implemented. So instead of going for like approach using arrays or linked list, here what I have done is like I'm trying to show that implementation of that particular tree using this heapq library. Okay, so this from heapq library, I am calling three methods: heapify, then heap push and heap pop. Okay, so pushing is adding an element to that heap, and popping is like removing element from that pop. So basically, I'm defining certain iterable. So basically, it's array storing into heap, converting that iterable into heap. If I am converting into heap, basically I'm creating a tree presentation, and then I am adding elements using this heap push function method. Okay, and it need two things: the heap that we have created and the element that we want to add. So I'm adding this four elements over there: 10, 30, 20, 400. So according to our convention, minimum element should be parent node, and child node should be like in its like branches. Okay, so second element is like bigger than 10, so it will go into left branch. 20 is something like means decide like where exactly it should go. So it will check whether 20 should go into like, I mean, 20 is like less than 30, right? So it will go in parallel to 10 only. Then 400. So it can go on like either of that, either on 20 or 30. So this heap push will happen, and it will try to make that as like balanced tree. Okay, so this is a heapify operation, and then there is a popping thing. Okay, so we are popping the last element from, or like minimum element. So basically, whenever do heap pop, so element at the 0th level will be like removed. Okay, so it's quite similar to that stack thing, or like means how should I call it, stacking, rather queue thing. Okay, or like array means first element or oldest element will be deleted, or minimum element will be deleted using this heap operation. And when I print this entire heap, you can see it to be like head value of heap to be like 10, then entire heap would be like 10, 30, 20, 400. And after deletion of after that popping operation, 10 will be removed, and then it will be like 20, 30, 400. Okay, so that's how this thing is getting done. Okay, so again like 20 will be like move up, because this entire heap will be like adjusted automatically, because there is no parent node which is smaller than 20 and 30. So in this case, 20 will become new parent, and 30 and 400 will become like new childs. So this is how like we are implementing min heap. And whenever it comes to max heap, it will be same thing. Okay, the only thing is like we just need to multiply like this inserting element with -1, and at the time of pop means we don't have to do anything. What will happen is like maximum element will be like deleted. So we will create like iterable heap, we will heapify that thing. So basically we will create that balanced binary search tree, and then we will like add element with 400 will be like root node, and new element will be added in child node. So smaller elements will be there in child nodes, and that's how we will implement this thing. Like 400 will be parent node, then 10, 30, 20 will be there, and that entire modifications or implementations will happen. And then we will push like bigger element. So basically using this heap pop. So basically whenever you create heap 0, so you will find like minimum element over there. And since we are multiplying it with -1, that's the reason we are getting 400. That is the maximum element pop. And when we print this thing, we will get like head value of heap to be like 400, and then like 400, 30, 20, 10. So this is how that heap has been created. And when we like pop that 400 from that list, again like new thing will be 30, and then 10 and 20 will place into either branches. So that's how this heap is being implemented. So seeing the thing is that like insertion and deletion is quite easier with like this these non-linear or unordered data structures, but searching in worst case can be equivalent to heap only, sorry, arrays only. So that's the reason we try to go for heap, because that's how means we can get like certain things speed up. Guys, we might need to join again. Yeah, do you have any questions?
No.
Okay, probably then just let's keep going. Next thing is hash maps or hashing operations. So thing is that we were discussing this thing in last lecture only. Like whenever particular array is quite big and there are a lot of numbers, so in that situation, it becomes quite difficult for us to do that searching thing quite effectively. Okay. So in that situation, what we can do is means thing is that when we talk